All right, let's talk about Unit 6 bonding. So there are many different types of chemical bonds that can be made, but first we need to talk about two types of elements to help us determine what kind of bond they are going to be created. So there are two different types. There's metals and there are nonmetals. So the entire periodic table can be divided into these two parts. And so if you look up here on the periodic table, they are divided by that thick black staircase, okay? And these are what divides your metals, which are on the left-hand side, and your nonmetals, which are found on the right-hand side. Okay, so there aren't that many nonmetals, so they're very easy to spot. The nonmetal that most people forget about is hydrogen over here. So don't forget that hydrogen is a nonmetal, but the rest of them are metals on the left-hand side. So if we were to look at these elements, you need to quickly determine if they're metals or nonmetals, right? So carbon is the letter C. You take a check as to where it is. Carbon is right here. So you know it is going to be a nonmetal. So you would write nonmetal here. Some of the elements you might not be familiar with, like NB, right? And so you need to sort of look for it, okay? Niobium is right here. It's element 41. It is a metal. It's on the left-hand side of the staircase, okay? So I'm gonna give you a second to figure out the rest of these. So you can just take a quick pause and try to find the next four on your own. And I'm going to show the answers in just a second. Okay, so here are the rest of the answers. Remember, sodium is not the letter S, but it is Na, so it is a metal on the left-hand side. Silicon's a non. Tin is a metal. Remember, hydrogen is one that people most commonly miss, but it is a non-metal. Okay, so a compound is a pure substance that is formed by the combination of two or more elements that are bonded together. We achieve this by reactions. We talk more about reactions next unit. But basically, bonding occurs because all atoms always try to have a full outer shell to be stable. Remember, this is our octet, right? Having 8 valence electrons, like a noble gas, makes it really stable. So to achieve this, there are 3 different types of bonds. The first one is called an ionic bond. This is when you have a metal attached to a non-metal. An example of this is salt, NaCl. Here, electrons are transferred, okay? Meaning that metals are gonna lose electrons to achieve that octet, and nonmetals are gonna gain those electrons, right, to achieve their octet. So the metals are gonna give up their electrons and give them to the nonmetals. It's like one man's trash is another man's treasure. So some of the properties they have is that they're brittle, they have high melting points, they're considered electrolytes, meaning they have charges. We talk more about this in the next unit, so I won't worry too much about it. Covalent bonds is when you have non-metals that are bonded together. We're only going to focus on 2 non-metals being bonded together, even though there could be more. An example of this is water. Hydrogen and oxygen are both non-metals. Here, electrons are shared. So they basically hold hands and share so that they both can achieve an octet by sharing electrons. This is basically the opposite of ionic compounds. They have low melting points, are non-electrolytes, no charges, no one's giving up anything because everything is shared. The next one are your metallic bonds. This is when you have a metal usually bonded to itself, or it could be bonded to another metal, but generally speaking, it's talking about to itself. Like silver is bonded to itself and silver can bond to itself again. So it's just continually bonding to another metal, right? An example of this, or a special property that metallic bonds have, is something called the sea of electrons. This is a phrase you really have to know. Okay, so I'm gonna highlight this box here so that you remember. But this is basically saying that electrons travel all over this metallic bond. So that's why metallic bonds have very particular properties, like they're very malleable, meaning that it's easy to bend. There are ductile, meaning that they can form wires. And I know this got cut off, but it's like conductive, right? Meaning like you can form electricity and things like that. The reason why this is the case is because electrons are sort of like constantly moving. Like they don't really stay in one spot. They have the ability to like swim around the entire thing, which is why metallics have like a luster as well. They have a shine to them because when light hits them, because they're moving around, they reflect that light back and it's very shiny. Okay. Probably watch a video about sea of electrons when we head up into class. So we'll talk more about that in class. Okay. So how can you remember ionic or covalent bonds? Metallic bonds are really easy because it's like, you know, metallic metal, so it's bonded to itself. But there's a phrase here called I'm on CNN to help you remember. So I meaning it's ionic bonds, right, are made out of metals plus non-metals. And then this C stands for this covalent bond is made out of these two N, right? It's non and non. So when you are going through compounds, it's best that you like constantly like think about, okay, is it metal? Is it non-metal? Is it ionic or is it covalent? Okay, so for example, here you have a compound, CS2. So your goal is to figure out, okay, so carbon is my first element and sulfur is my second element. Then I look up at the periodic table to determine what it is. So carbon is a nonmetal and sulfur is also a nonmetal, right? So I know that this is a non and non. Two nons, right, are as what type of bond? It's covalent, right? So you know that they're going to be sharing electrons. Okay, so go ahead and try the rest and on your own, and then you can pause it really quick and then play it when you're ready to see all the answers. Okay, so here are the rest of the answers. So you had your ionic bond because metal, non-metal, metal is metallic, and non is covalent. Okay, so if you have any questions, make sure you mark it down so you can ask your teacher. Okay, so right now we're gonna like zone in and focus on ionic bonds. Remember that ionic bonds is when you have a metal with your non-metal. Okay, so here metals are gonna lose, right? So remember, if you lose electrons, negative, right? You lose electrons, you become more positive, you become a more positive person. Non-metals do the exact opposite. They gain electrons that are negative. So if you have more electrons, then you become negative. You recall, right, from before that opposites do attract, positives and negatives do attract, which is why metals and non-metals, they like to stick together because opposites attract, okay? There are some vocabulary words here that we need to know. So should have learned these already, right? Ion is a charged particle. So you either have a cation or an anion. Remember the cation has a T that looks like a plus sign. This is like probably the easiest to remember. Anion has that negative, right? Like that. So like right here, you see that this has a negative. So you know this is an anion. This doesn't have anything, so it's neither. That means it is neutral. This has a negative, so you know it's an anion. And this is a positive, so you know this is a cation. So I usually write it like this to remind you. It's a cation, right? It's not a cation or an anion. Ooh, yikes. Cation and ion. You want to hear that word ion in the word, okay? All right, so then in order for us to think about ionic bond formulas, we have to think about whether something has a cation or an anion, because ionic bonds always have a cation and an anion. So when you're given a formula, then you have to determine what kind of bond it is and then determine if it has a cation or anion. So the first thing you want to do is determine this side. What type is it, right? So you got to look at your elements here and then determine, right, what type. So you look at aluminum and you like, and here's sulfur. So I'm gonna go ahead and peek at both at the same time really quick. So aluminum is here. So aluminum is a metal. Sulfur is a non-metal, okay? So you gotta use your periodic table all the time. So here we have a metal, that's aluminum. Sulfur is a non-metal. So when you have a metal and non-metal, you know that it's an ionic bond, right? So you can pause really quick and like determine this really quick if you want to, and then check your answers just a second. Okay, so here's a rest. So you got your non-metals. Non-metals are your covalent bonds. Every time you have a metal involved with a non-metal, you know it's ionic. Okay, so when you have a covalent bond like this, you do not have a cation and anion, right? So remember, if you spell this word out, ionic, right? What does this word spell right here? It spells the word ion, right? So it has a cation and an anion, right? The word ion is in all the words, but when you spell out covalent, right, it doesn't have the word ionic in it. So it doesn't have a cation or an anion. So you like cross these out because you're like, this doesn't exist. Anions don't exist with covalent compounds, okay? So once again, if you spell out the word ionic, then it becomes really obvious, right? That ion, ion, ion. So you know cations are positive, you know anions are negative. Okay, so following the information that you learned last unit, okay, then the question is, how would you write your cations and anions? So you know the first element here is always your cation. The second element is always your anion. Okay, so you're gonna write aluminum here and you're gonna write sulfur here. But now we have to include the charges, okay? So aluminum is in which column, right? So we learned that before. Aluminum's in the third column, so it's gonna lose 3 electrons. Remember, when you lose negatives, you become positive, right? You have 3 more protons than you do electrons. So just a quick reminder, right? So aluminum originally had 13 protons and 13 electrons. In order to become a noble gas, it's going to lose 3 electrons and now it has 10, right? So it has 3 more protons than it does electrons. So that's why you put positive 3 in the corner. So same thing with sulfur really quick. So sulfur is a non-metal. So if you look up here, sulfur has 6 valence electrons. So it's going to gain 2 electrons to have a full octet, right? Look like a noble gas. So just to recall really quick, right? Sulfur has 16 protons and 16 electrons normally. But if you gain 2 electrons, now you have 2 more electrons, negatives, than you do positives, which is why some people write like 2 like that. So 2 more negatives than you do positives. And same thing with here. Some people write it like aluminum 3 plus right here because it's saying you have 3 more protons than you do electrons. Either way, it means exactly the same thing, so no big deal. So how about you pause really quick and try this last one on your own. You know this is an ionic compound, so you know it has a cation and anion, to see if you can write the charges following your note. Okay, so it should look like this: a positive 2 for magnesium, negative 2 for oxygen. In this chart, you're not going to see a metallic bond because they don't have any cations or anions or anything like that. And the most popular 2 type of bonds we're going to see is the difference between ionic and covalent. Okay, so now we're going to move on to Lewis dot structures. Okay, and we're going to keep it simple. Okay, so let's talk about what they're going to look like. So lithium, according to the periodic table, lithium is in the very first column, right? So just taking a quick peek up here, lithium is over here. It has 1 valence electron, okay? So you learned this in the last unit, but lithium has 1 valence electron, so you draw it like this, okay? In order to become stable and have that full octet, it's gonna lose 1 electron. So it loses that, which is why lithium becomes this, right? Magnesium has 2 originally, so it loses those 2, right? And it becomes magnesium positive 2, right? It has 2 extra protons. Aluminum, same thing, right? It originally has 3 because it's in the third column, but it's gonna lose these 3 to become this, right? So it has a stable thing, right? So fluorine And oxygen and chlorine on this side do the exact opposite, right? So fluorine already has 7. That's why it's in the 7th column, right? And so it's going to do what instead? It does the exact opposite, right? These non-metals gain electrons and these metals are going to lose electrons, right? So here it gains 1, right? So that fluorine gets what? Has all 8, right? It has this -1 charge. Usually you will always see it like drawn, it's like really fancy. It has like brackets, it has dots, it has the charge in the corner. We always say that metals get fully naked because it loses all its valence electrons, but non-metals gain all the clothes, so they are fully dotted up. Okay, so just really quick, just to show you like visually what it looks like. So oxygen here originally has 6. So if you have 6 and you want to get to 8, you gain 2. So if you were to see this like in its full glory here, you would see 8 dots and -2, it gained these 2 extra electrons. Chlorine's the same thing here. Or actually, I prefer to do another example here. So like if we were to do like nitrogen, nitrogen has originally 5, but to be, get a full octet, right? And to become more stable, then it's going to have to gain how many then? It's going to gain 3, right? So now nitrogen now has all 8 and it's like super happy. So you draw it in all its glory and it gained 3, right? So this is what it looks like. So metals are constantly losing. So where do those electrons go? The non-metals are going to scoop them up, right? So that they can have a full octet. So it's a win-win situation for both, right? So how are we going to use that information to now create ionic compounds? Okay, so in order to do that, okay, here's an example. I'm going to do a few and I'm going to have you do a few. So here's lithium and here's fluorine, right? It already tells us we have one of each, but just in case we didn't have this number, right, this is how you would think about it. Lithium has 1 valence electron because it's in the 1st column, right? And fluorine is in the 7th column, so it has 7. They're both unhappy, so they're going to do a transfer of electrons. So what's going to happen? How do they both win here? Lithium wants to get rid of this. Fluorine wants to pick some up. So you're going to take this electron and lithium is going to give it to fluorine. Okay, it's going to give it away. Goodbye, right? So then how do they win, right? So then if you look on this side, you have lithium, right? Whoops. Lithium now has a +1 charge and fluorine now has a -1 charge because lithium lost 1, but fluorine gained 1, right? So here now, all you're trying to do is when you're making an ionic compound is you got to make sure that all parties are happy, right? So you want to make sure that these charges in the corner actually cancel out, okay? So when they create an ionic bond, you want it to become a neutral compound. So positives and negatives have to cancel out. Does +1 cancel out with -1? Yeah, they do. So how many of each do we need? For every 1 lithium, we need 1 fluorine. Okay, so how would we write that? You would write L, I, and you would write F. So you would say like what people might want to write is you have 1 lithium and 1 fluorine like this, but we never write ones in chemistry. So this becomes this with no ones. Okay, it just becomes LIF, right? So here's another example. Let me just do a few more examples here. So in this next example, you have magnesium oxygen. Doesn't tell us how many we need, okay? So magnesium is in the 2nd column, so it has 2 valence electrons. Oxygen has 6, so 1, 2, 3, 4, 5, 6, right? So magnesium is going to lose electrons, right? Metals are going to lose electrons, right? So the whole point is to lose on this side. This side's going to gain electrons so that both parties are happy. So magnesium can give away 1 of the electrons to go here. So it's going to give it away, and this electron can go over here to give it away, right? So when it does that, what do you end up, right? Magnesium loses 2 electrons, right? And oxygen will gain 2 electrons. And the question is, do these cancel out, right? Does this cancel out with this? Yeah, so you only need one of each to achieve neutrality, right? So that means that when you write your compound, like I said before, like no one writes like MG101. That looks weird. So everyone writes MgO like this. So this is what our final compound would look like here. So what's an example of when it does not actually become one-to-one? What does that look like? Well, let me show you an example down here. Okay, so here you have aluminum and chlorine. Okay, so aluminum, chlorine, aluminum is 3 valence electrons, is in the 3rd column, and chlorine is in the 7th. 1, 2, 3, 4, 5, 6, 7. Okay, so aluminum wants to get rid of their electrons, but chlorine wants to pick them up, right? So you have metals that want to lose, non-metals that want to gain. So aluminum's like, yeah, here, take one of my electrons. There you go. Here, I'm going to give it away to you. Now, chlorine then has 8. That's great. But aluminum still has how many? Yikes, it still has 2. And it's like, oh, I don't want that, right? So that means you need another what? Another chlorine has to come over here, right? So another chlorine has to come over here. And aluminum's like, ooh, another chlorine. Then I am going to take this electron and give it to this chlorine. But now it still has what? It still has another electron left. So you need another chlorine. So another chlorine pops by. 1, 2, 3, 4, 5, 6, 7. And that means this last electron can get to this chlorine, right? So now when that happens, then what's the ratio? How many aluminums to how many chlorines to achieve like our neutral compound here, right? So another way to like think about this is that you know aluminum's in the 3rd column. So you know that it's going to have a +3 charge, right? So like just going back to our periodic table here, remember, right? I didn't write this before, but if you have this periodic table, remember, it's always you lose 1 electron, you become +1. You lose 2 electrons and you become a +2. You lose 3, it's +3. 4 is sort of whatever, it doesn't really happen here. Depending on your teacher, sometimes they write ±4, even though it'll never actually happen. And then it goes backwards. If you have 5, you're going to gain 3 electrons. If you have 6, you gain 2. If you have 7, you gain 1. 8 means nothing, right? So it goes 1, 2, 3, 4, and then it goes 3, 2, 1, right? So when you're looking at this example here, aluminum's in the 3rd column, it's going to lose 3. Then you're like, okay, chlorine is in the 7th column, so it's what? -1, okay? So it gains 1 electron. And you look at this and you're like, does this number, does this charge cancel out with this charge? It doesn't, right? So you're like, that's not gonna fly, because this aluminum has a +3 and this chlorine has a -1. That means what? You add another chlorine that is going to gain another electron. And so you're still counting and you're like, that still does not cancel out. I still have a +3 and I have -1 and a -1. Still doesn't cancel out. So you need another chlorine. So now you look at it and you're like, hey, these cancel out. So what's the ratio then between aluminum and chlorine? For every 1 aluminum, right, I need how many chlorines? 3. So then how would you write it over here? So if you write, I need 1 aluminum for every 3 chlorines, right? Remember, we don't write 1. So it looks like what? Al, Cl, and we need 3 of them. So we always put it like a little subscript on the bottom to indicate how many of those elements we need to create a neutral compound, okay? So you can try some of these on your own, and then you can pause. So pause right now so you can try it, see if you can figure it out, and then I'll write some notes here so you can check yourself. I also want to point out that these drawings with the arrows are like completely like optional. They're just like drawing you to give you like a visual like aspect of what's happening, but you're not, you don't need to draw the arrows per se. Okay. So like you can think of these as like scratch work, because eventually the goal is to be able to do this with minimal scratch work. Okay. So try it, pause it, try it, and then check your answer. All right, so let's check your answers. So here you needed 2 lithiums for every 1 sodium for them to cancel out. The next one, you needed 1 magnesium for every 2 chlorines for it to cancel out the charges. So it looks like this compound right here. Here it's already 1 and 1, simple enough. But remember, we don't write ones in our compounds, so it's just KBr. This last one I wanted to do together because it was a little tricky, and so hopefully some of you already figured it out. So aluminum's in the 3rd column, so it's a +3. Sulfur is in the 6th column, so it's going to gain 2, -2. So remember, you have your periodic table with your charges. So look up here, right, to get the numbers. Okay. Now, this is not even, right? It's not going to cancel out here. So we need to add more elements. So you're like, okay, I need more negatives. So you have to put a sulfur. For every sulfur, you have to put -2. There's no such thing as sulfur with like a -1, right? Sulfur is in what? The 6th column. So you have to put a what? You have to put -2. Like there's no choice here. It's always a -2. So then you write this and you're like, okay, still not even. So now I have a +3 on one side. I have like 2 -2s on this side, right? Total of -4, still out of balance. So I'm like, okay, I need another aluminum here. And aluminums are always what? Because they're in which column? They're always +3, right? So it's still not even. You're like, oh my gosh, this is going to go up forever. It's not. There's always an end. So you add another sulfur here, which is a -2. Okay, so these numbers in the corner can never change. They always belong to the same element. The charges are always same for each element. So now you check. You have +3, +3, 6. You have -2, -2, -2, 6. You made it. So what's the ratio between these elements? For every 2 of these, I need 3 of those. So how would you properly write it? I need 2 aluminums for every 3 sulfurs. Perfect. Good job, y'all.